To engineer an end-to-end machine learning pipeline, we will build a model to predict house prices using a raw dataset from Kaggle. We start by defining our variables. The independent variables, known as features, are the inputs we use to make our prediction, things like square footage and location. The dependent variable is the target we want to calculate, the final house price. Because our target is a continuous numerical value, a specific dollar amount, this requires a regression model. This contrasts directly with classification, which sorts data into discrete categories. This diagram outlines the data science project lifecycle, moving sequentially from descriptive to prescriptive analytics. Focusing specifically on the predictive analytics phase, we see exactly where our problem fits, using regression analysis to forecast future outcomes from historical data. Accurately defining problem constraints in Step 1 dictates the entire mathematical architecture and guides the specific algorithms we select for the rest of the pipeline. We begin by initializing our Python tool stack. We use pandas to structure data, Seaborn for visual analysis, and scikit-learn to access algorithms. The immediate task is reading the raw CSV files and using pandas to convert them into two-dimensional tabular matrices, known as data frames. Once loaded, we must inspect the data using specific commands, primarily df.head and df.info. This matrix represents our dataset's dimensionality, where horizontal rows are individual samples and vertical columns are features. This inspection phase exposes structural anomalies. Empty cells highlight missing values, or nans, while text strings clearly stand out against the required numeric formats. From there, calling the df.describe method evaluates the base statistical distributions of the dataset, including the mean, standard deviations, and quartile ranges. The conclusion from this initial ingestion is clear. Real-world data is structurally incompatible with mathematical algorithms and requires immediate, rigorous preprocessing. We move into Exploratory Data Analysis, or EDA. This is where we diagnose the dataset to uncover skews, pinpoint extreme outliers, and identify relationships between our variables. Plotting a scatter plot, for example, immediately reveals the base linear correlation between a single feature, like square footage, and our target price. We also look for multi-collinearity. Generating a correlation heat map exposes redundant features that move together, which can artificially inflate our model's confidence. This leads to a fundamental prerequisite of machine learning. Models can only process numerical tensors. Feed an algorithm strings of text or missing data, and it will completely fail. To handle missing values without sacrificing valuable rows of data, we use imputation. A common technique is filling the gaps with the statistical mean of that specific column. This animation demonstrates one-hot encoding, a method used to convert nominal categorical data, like neighborhood names, into machine-readable binary logic, splitting one column into multiple columns of zeros and ones. Continuing the visual comparison, we see the necessity of feature scaling, applied here through standardization or normalization. Without scaling, columns with massive magnitudes, like a lot size of 10,000, will mathematically overpower features with small magnitudes, like a bedroom count of 3. This biases distance-based algorithms and ruins predictions. Ultimately, EDA and preprocessing are about translating chaotic human attributes into a pristine mathematical matrix, perfectly formatted for algorithmic ingestion. Before training begins, we must enforce a strict isolation between the data we use to train the model and the data we use to test it. This block diagram illustrates that strict split.
Training an algorithm on the exact same data used to evaluate it causes catastrophic overfitting, where the model simply memorizes the answers rather than learning the underlying patterns. With the data safely partitioned, we introduce our first model architecture baseline, simple linear regression. This scatterplot shows the goal of linear regression, calculating a red line of best fit that bisects the data points. The vertical dotted lines represent residuals. A residual is the actual geometric distance, or error, between our prediction line and the true data point. This graph details the math behind ordinary least squares, the engine of linear regression. It works iteratively to minimize the sum of those squared residuals, optimizing the equation based on the random error calculated between observed and predicted values. We contrast this linear approach with tree-based models. A decision tree does not draw a straight line. Instead, it routes data through a series of discrete, conditional threshold splits. This animation represents a random forest. By aggregating multiple weak decision trees together, The model combines their outputs into a single, highly accurate ensemble prediction. Model training is an exercise in pure mathematical optimization. The objective is to discover the specific function that maps our input tensors to our output targets, with the absolute minimum amount of error. Selecting the best model relies strictly on quantitative evaluation metrics. We strip away all human intuition and look directly at the math. This table breaks down our primary grading tools: mean absolute error, and the top row, mean squared error. Notice the squared exponent in the MSE formula. Because of this squaring operation, mean squared error penalizes large prediction errors exponentially more heavily than small ones. We then take the square root to get RMSE, or root mean squared error. This provides a practically interpretable metric, allowing us to say, this model's predictions are off by $20,000 on average. To improve that metric, we adjust the model's architecture. We differentiate between parameters, which the model learns automatically from the data, and hyperparameters, which the engineer sets manually, like the maximum depth of a decision tree. We optimize these settings using a grid search. This algorithm systematically tests thousands of different hyperparameter combinations, seeking the exact configuration that yields the lowest RMSE. Rigorous hyperparameter tuning mathematically guarantees that the model extracts the maximum possible signal from our data without tipping over into memorizing the noise. This data table compares the final evaluation metrics between our tuned linear regression, random forest, and XGBoost models, revealing the lowest RMSE value. The ensemble model is the definitive winner. We deploy it based strictly on this superior ability to generalize its predictions to unseen data. Transitioning to the deployment phase, we prepare our Jupyter environment to execute a live prediction on a new house. We initialize the final .predict function on our deployed model, a brand new vector of house features containing unseen square footage and location data is passed directly through our exact preprocessing pipeline and fed into the frozen model. The execution yields our final output variable, a highly precise, single continuous numerical value representing the projected price of the house. We began by defining strict problem constraints, encoded real-world variables into numerical tensors, and continuously optimized a mathematical loss function to reach this exact output. Applied machine learning is an entirely mechanical process. It is the rigorous, sequential application of data geometry and statistical calculus to accurately predict the future.